Okay, so hello everyone. So welcome to our this week Rogers Efficient AI Seminar. And today we're very glad to have the Professor Hongxiang Fan from the Imperial College London to give us this talk about how to push the efficiency frontier of the AI. And Professor Fan is currently assistant professor in the Department of Computing at Imperial College London. And he has been awarded the Microsoft Research Faculty Fellow and holds a visiting fellowship in the Department of Computer Science and Technology at the University of Cambridge. Before joining his current positions, he was a research scientist at Samsung AI Cambridge, working on mobile NPUs. And his research is pretty broad and focused on computer architecture, machine learning, and quantum computing. And he has received the Best Paper nomination as ASAP 2029 and the FPT 2019. And he also serves as program chair of the ASAP 2026 and the TPC meeting for several prestigious conferences like ISCA, DAC, and so on. So now let's welcome Professor Fan to give us this talk.
Thanks. Thanks, Professor Yuan, for the kind introduction. It's my first of all, it's my great pleasure to have this opportunity to give this guest talk. The title of my presentation is Across the Core Design Pathway for Pushing the Frontier, the Efficient Frontier of AI. I'm an assistant professor at Imperial College, and my group is named Intelligence Heterogeneous Computing Research Group. Okay, so let's get started. With recent years, we can see the influence of machine learning across multiple domains, including healthcare, science, like people talk a lot about AI for science, and education, content creation, like video generation. I think now it's a very hot topic, and also AI for help student to do writing. And some other domain, manufacturing, finance. However, one thing we notice in this AI algorithm is algorithmic complexity is increasing dramatically in the past decades. And if you look at give a plot to understand the amount of parameter and the amount of compute in this AI era, so you can see this large language model scaling law. The scaling law is driving this increasing complexity in terms of both parameter and the amount of computation. And one example, the recent example is Kimi K2.5, which has trillion level parameters. So that means this AI, although it's very powerful, but it also introduces a large amount of parameters and computations, which cause a significant challenge. So, however, if we look at this underlying computer architecture level trend, the first thing we notice is the Moore's law is slowing down. So this is the plot for CPU. So if you can see here after the RISC, and you can see the performance of CPU is gradually slowing down, especially after 2000. And you might challenge me, okay, how about GPU? We still have GPU. But GPU layer has its own issue, which is the energy efficiency. So if we're going to train let's say, not billion level model, just a BERT, so the training from scratch, it will cost the carbon emission of 5 car lifetimes. So it means the GPU is not an energy efficient solution. And this can be also evidenced by the recent move from NVIDIA. They bought Grok as their inference chip, and they provide the heterogeneous inference system combining GPU and Grok system. So another key issue, apart from this energy and environmental issue, is the affordability of AI. So if you look at all these large language model or foundational model companies, one common question all the VCs or investors will ask is, are they really making net profit? So this is not just for so in here I try to investigate what is the root reason for this negative net profit. So there are two costs in these foundational models commonly. So the first one is training cost, because for this model like OpenAI or Anthropic, they need to keep their model to be frontier model, right? For example, in the benchmark, they will need to have a very good score. So they will need to invest a lot of money in the training to scale their model. And also for the inference cost, you need to purchase GPU to serve this AI inference or large language model inference. So it will kind of introduce some capital cost and also operational cost, like electricity and infrastructure cost. So these two costs make these foundational company, they're actually not making net profits. And this is kind of people say AI bubbles. So is this going to be better in the coming years? My personal prediction is no, because the model is keep scaling. Unless we can see some very risky or very advanced breakthrough in architecture level, I don't think this will kind of become better in the coming years. And so under this setting, so like even these foundational models, foundation model companies, they spend a lot of money in training their model, and they provide API costs. So in the an early stage, they try to lower the API cost to attract more users, even like under this like what they say is price battle. So we still cannot afford some commonly application like OpenCloud, which is very hot recently. So this is the second issue, affordability. Even the AGI comes, can AI really influence our everyday's life? Because I'm very skeptical about this because of affordability of AI. So this becomes this efficiency issue and the affordability issue comes the core idea or the root of my lab in driving or pushing this efficient AI. So the core belief we have here is the cross-stack optimization can actually push the efficiency frontier for AI. So in this slide, I shows the research in my lab from algorithm level, system level to architecture level. So in the algorithmic level, we're exploring efficient machine learning algorithms, like we study this power prompt coding, which break the autoregressive generation paradigm. And we also explore this progressive precision lowering, which means during the decoding, we can switch the precision when like we feel like the generation will be more robust to error. And we also explore some efficient language model variant like diffusion language model. At the system level, we are also exploring how to optimize the kernel design as well as the system level scheduling. So this comes to our S+ paper this year. So are based on VLM. So we have some plugin to enhance the VLM serving engine to support the test time scaling or reasoning. And we also are studying the KV cache eviction to reduce the memory overhead of large language model. And in the underlying architecture level, we also explore some fundamental innovation in the underlying hardware, like the reconfigurable architecture for GPU or domain-specific accelerator. So in today's topic, so I will introduce one core design. The core belief we have is the code algorithm and system core design. So this is a line of work done by my first PhD student, Mark Chen. So we have the publication in both NeurIPS and S+, and we open source the code in both papers. And before I introduce this work, this is my great team. So you can see we have around 4 PhD and IAs, and in the coming October we have up to 10 PhD and IAs. So okay, let's get started. So the first one is how to make large language model reasoning, or we call machine thinking, more efficient. So here I use a screenshot from a movie, The Imitation Games. So the officer asks Turing, can machine ever think as human do? And the answer from Alan Turing is the machine thinks differently from a person. So, however, if you look at existing large language model reasoning, because when we design large language model, we want this language model to imitate the human thinking process, which is called a long chain of thoughts, which means before giving a real final answer, we have a sequence of reasoning trace, very long sequence trace, single trace, to iteratively thinking, okay, whether what is the time to give the final result, and there are a lot of logic goes here. And however, this long COT has several issues. The first one is this text-based long COT will introduce a phenomenon called output token search. So basically, it will introduce over 52 more tokens in a specific task like math and reasoning, and introduce significant energy and latency overhead. And if you look at this figure, I put the line chart I put here. So you can see if we use this at the beginning, so we have this number and we have this ik, but when we try to use this reasoning, it can dramatically increase. So the leftmost points is the one without any reasoning and long COT enable. And when we try to enable it, you can see the output token, number of token is increasing dramatically. So it basically increased the output token by 52 times in a specific task. So this inefficient long COT make us to think about what is a way machine can think. So the first thing come to our mind is latent space reasoning. So the key idea is instead of reasoning in this text space, like you show this text-based reasoning trace, can we just reason over the latent space vector instead of text-based tokens? So, however, we found the performance is much worse than text-based reasoning. So we are still exploring this direction of and explore this latent space reasoning even for multimodal reasoning. But we just found in general, without any retraining or post-training, the performance of latent space reasoning will be much worse than the long text-based long COT. So this is the one of the technical routes we tried last year to explore this direction. And the other direction we're thinking about is called power thinking. So it's also only only machine can do. Or I put here, so in Marvel's world, so you have Doctor Strange. So you calculate the multiverse in parallel. So calculating different possibilities. So it's basically something we think machine can also outperform humans. It's called with power thinking. So the key idea is to generate multiple reasoning traces instead of just one long COT. So here I use an example of Bing search with a very basic or standard test time scaling approach for power thinking. So as you can see here, so if you have this question, so each node in this graph represent a thinking step. So first you have the first thinking step, you kind of generate 4 thinking steps in parallel, and you call a verification. So this verification can be, for example, another process reward model, or any, for example, neuromorphic or like any like verification methods. So you call this verification and you get the score or metrics, and you select, for example, the first and fourth, and you keep generating the next leaf or next level. So it leads to a second thinking step, and so on and so forth. You do this reasoning, thinking, and verification process iteratively and get your final answer. For example, second nodes in this graph. So this is the Bing search, which represent an extreme case of power thinking, which means in each step you do verification, you do selection, and you continue to generate different thinking steps. And the other extreme scenario is best of N. So basically, you don't do any intermediate evaluation. You just do this verification towards the end. So it's more like full complete reasoning trace and do one selection. So these power reasoning represent the most common and the power thinking paradigms. So in the first New Race paper, So we're trying to think about whether these two representative thinking paradigm is already optimal. So to answer to explore this objective, so we actually ask ourselves three research questions. The first is because as I mentioned before, there's a verification process which you need to verify every step. So the first question is the current verification granularity, which means one step in the bin search scenario, or the whole response in the best of the scenario, are they already optimal, or are there any other approach we can do this more efficient verification to improve end-to-end system performance? The second research question we ask is, what is the impact of verification on the system performance? Like whether they are really the performance bottleneck from a system perspective, because most of the algorithmic people or algorithm people, they only care about accuracy or the theoretical flop reduction. And the third question we are asking is how should we decide the optimal verification granularity if, let's say, for the first and second research question, our answer is yes. So how can we design the optimal verification granularity during the runtime? So to answer these three research questions, we start by the first one. So we start to test in this test set of Math 500. We try to uh, adjust or try to test all the possible verification granularity. It can be one step, two step, three step. We try all these verification granularity. We see what if we are Oracle, if we know what is the verification, optimal verification, what is the performance upper bound we can achieve by this by adjusting this verification granularity. And the answer to us is the current one-step or whole response test time verification is not optimal because we can see from the line chart here. So the purple line is the performance upper bound, which means we still have some improvement space we can squeeze. So the conclusion or the insight from this experiment is we need a better compute time, scaling, or verification granularity because it can improve the accuracy as well as reduce the theoretical performance, the theoretical computational complexity represented by the flops. And the second is we measure the real execution time. So we try to find out what is the system overhead goes beyond the theoretical flops. What is the system overhead of running this verification or verifier? So as you can see here, so when we so in here, if we set the verification granularity as 1, as this very light purple line at the top in this line chart, we can see it actually increased the average time of this test and scaling a lot. So the answer for the second research question is the verification when we do per step, it actually introduces a significant overhead on the overall system performance, which is latency. So based on this research question 1 and research question 2, we know first there are some design space or there are some optimization space we can explore. And the second verification can actually also affect this system performance. We now answer the third research question, how should we design the optimal verification granularity? So to address this problem, we propose a method called adaptive or dynamic variable granularity search, which means during the runtime, we dynamically adjust the verification according to the task characteristic. For example, if this prompt is, for example, decided by another, for example, language model is a difficult task, we can based on this difficulty to set how many how fine-grained our verification needs to be. So by testing this simple but effective approach, we found this we call it VGS. So this VG search, sorry. So we call this VG search can achieve over bin search and best of n while reducing the theoretical flops by nearly half, 50%. So this is the first algorithmic level exploration. So we do some performance profiling on like how different factors will affect the algorithm as well as the system performance. After this new risk paper, there are more content in the original paper. So I encourage you to read original paper, but here I just put the key insight. So after this Norris paper, we found very interesting another insight, which is this power thinking is actually bring higher improvement on small language models, for example, 7 billion models. What I mean here is the performance improvement of Tesla scaling of small model is more significant than the large model. So this insight kind of motivates us to to explore another research question, which is if we have a 7 billion model or even smaller model deployed in the edge side or your like local workstation, and we enhance this parallel thinking, we enhance this small model with the parallel thinking paradigm, the Tesla scaling we developed in our new risk paper. Can this combination, small model plus Tesla scaling, beat the large model on the cloud? So this is the initial result we show here. So as you can see, so this green line is the VLM performance, and the points at the leftmost is the performance, the accuracy performance without test-time scaling on a small model, small language model. However, if we apply this parallel thinking by controlling how much parallel generation you will have, so it kind of gradually increase the accuracy, and it can actually match the cloud accuracy. So here, the cloud accuracy we put in our SPLOS paper, I think we use GPT-4. Yeah, I think it's GPT-4 5.2 or 5.1. So you can see here, so by using this test size scaling on small model, we can actually outperform or match the accuracy of cloud models. However, one thing we notice is by using this test scaling, you actually increase the latency a lot. Now it's much lower than what should be accepted as a client, because for example here the green area is basically the gray area is basically the cloud latency region, like with the thinking mode of the cloud model. So we need to. So our objective of this paper is can we do system support to further push this performance like at the right top to this gray area in here. So this is what we want to achieve in this SPLOS paper. So the first thing we do is to improve. So basically, we want to push these the green points on the right to the gray region to be like acceptable by clients. What we need to do is we do performance profiling to see why this is so inefficient. Uh, so the first thing we did is we try uh, to kind of profile the GPU utilization. So as you can see here, the hardware underutilization is very severe because the irregular workloads. So let me explain here. So in the second plot, the lower plot I put in these slides, it shows the average and the max plot in each step. You can see when you compare the red bar and the blue bar, you can see a very large variant, right? So that means if we go back to this bin search, taking the example, so basically it means in every step, it contains different numbers of tokens. So they introduce, if you want to do a synchronization across one step, some reasoning path will need to wait the other reasoning path because they have the longer token consumption. So this is the one of the root reason why we have so low hardware utilization on GPU. So to address this issue, we inspired by the traditional speculative execution in computer science. So we call it speculative bin or speculative reasoning extension. So the basic idea is if we have a short reasoning path, we don't do the synchronization across different steps. Once the reasoning path is finished, we just keep generating. So a natural question you might ask is, what if this path is wrong? We didn't choose it. Yes, this is the worst case because we kind of waste our computation. But so according to our experiments, you can still get some decent performance gain because this is just the like possibility of how like this speculative execution will hit the right reasoning path. So this is the first contribution we made in our S paper. And the second contribution we made here is we realize the second inefficiency is called a suboptimal exploitation for dynamic prefix sharing. So prefix sharing is a very common technique in large language model inference serving, which means when you have multiple prompts and these prompts they basically have the same prefix, you can actually cache or store this common prefix part to avoid recomputation. And we found this prefix sharing in this serving system is very inefficient. And I will use an example to explain why. But let's move to the third inefficiency, which is because in here we assume our setting is edge setting. We have limited memory. So the third inefficiency is the constrained memory for multimodal execution. Because as I mentioned before, to do verification, you need to use another model, the small process reward model with some post-training. So in this case, you need to handle two models in parallel instead of one for reasoning serving. So so this to address the second inefficiency, as I mentioned before, the inefficiency of dynamic prefix sharing, we propose this reordering runtime reasoning trace reordering. So let me explain why the original approach will be so efficient for prefix sharing. So let's take an example of the first in the upper part of this figure, the first time step you first generate this ABDG. So this is your reasoning trace. Taking an example of Bing search, right? And in the second time step, if you decided to execute the second reasoning trace, so it basically is ACFJ, right? So ACFJ, which means if you have constrained or limited memory, you need to evict BDG. So this kind of waste of kind of caching opportunity. So instead, a better execution order is after execution the first ABDG trace, reasoning trace. So instead of executing the original ACFJ, so we basically can execute the ABDH because they have longer prefix for to maximize the prefix caching. So we do this reordering during runtime by collecting the runtime reasoning information. So this can actually help us to improve the memory management or caching efficiency a lot. So the third, as I mentioned, is the constrained memory. We need to handle multiple models. So in here, we use a very simple technique. We use the roofline model to allocate the KV cache. So which means, and we found the generator is more sensitive to KV cache than verifier. So we basically allocate more cache for this generator. So after all these three contributions, of course, there are some other technical details, but in here, I just highlight the most key idea in this paper. So there's other technical optimizations in the original S paper, but in this final evaluation, we're basically able to push this test time scaling curve with the system optimization to this dark green line. So which means we can actually have the same accuracy as the cloud model, and we also can keep the same the same accuracy as the cloud model can have. So in the original paper, we also test under different setting. For example, the model size of generator and verifier, and we test in different data sets in different hardware platforms. and to make the evaluation more comprehensive. But this is the key idea. This is one example of how we kind of use this algorithm system co-design. So as you recall, at the beginning, we tried to rethink the efficiency of algorithm, and we proposed one algorithm. And later on, we found, okay, this algorithm is still not very efficient in our GPU system. So we proposed some tailored system GPU optimization for that system, so we can actually make this um, edge uh, edge model to beat the cloud model with the same level of accuracy. So this is the one work, the first work I want to share today. And the second work I want to share is algorithm and hardware co-design. So recall the first topic is algorithm system co-design, which we have done last year. But here I'm going to share another work, which is called algorithm hardware co-design. But this kind of conclusion in this work is because this paper was published in Micro 22 when I was still a PhD student. So the conclusion is a bit already out of date, but here I still just want to show what is the key idea. Okay, so I will skip this motivation part. I think some this conclusion is already very obvious nowadays, but less obvious I think it's 4 years ago. So this is attention, the module of attention layer, right? So you have the multi-head self-attention layer, and you also have the feed-forward network. So, so they kind of occupy most of the computation. However, we found most of SOTA accelerator at that time, they only focus on attention without caring about the second part, the fully connected layer. So this is the key idea. So as you can see on this bar chart, so if we vary this input sequence, we can see different components is dominating under different input lengths. Like here, when the input length is short, the feed-forward network is dominating the execution time. However, when we increase the input sequence, the self-attention is dominating. So this is a key idea. So based on Adam's law, so we need to accelerate both parts together. And the key idea at that time is we want to use the sparsity to accelerate both parts. So here is the idea we want. So ultimate objective or the key idea is we want to find one unified sparsity which can apply on self-attention as well as feed-forward network. Because the motivation of the bar chart I just showed before, we want to achieve speed up across different input lengths. So for this unified sparsity, we want this sparsity to be applicable to FFN as well as self-attention, and we also want this sparsity to have the less hardware control overhead, because if you are talking about random sparsity, you kind of have some extra hardware or area control in your real chip. So this is the lesson we learned from the Samsung mobile TPU NPU. So at that time we found a sparsity called butterfly sparsity. So the basic idea here is let's assume the blue color is the non-zero value. So you have this metric. So the butterfly sparsity basically says, let's say if you have this dense matrix, you can basically decompose it into a series of butterfly matrices, and these different butterfly matrices, so they actually have different data access, right? And it's very regular. So this kind of gives us the chance to design a very efficient, which means we don't need very complicated control signal for irregular data strike or data access, because they are very regular. It's 2, 4, 5, it's 2, 4, 8. It's kind of two power a number. So this butterfly we found is very hardware friendly. As I mentioned, it can simplify the hardware control because it's more regular memory access. And we found at that time two technique actually has this butterfly sparsity pattern. The first one is called FFT, and the second one is called butterfly factorization. So let me introduce them one by one. So the FFT, which is a technique at that time proposed by Google. So they propose a network called FNet, which means they use this FFT to replace all the self-attention layers. So this is the first technique, but they still kind of use the fully connected layers. And the second technique is called butterfly factorization, which means it can be applied on feed-forward network to decompose the dense matrix into a series of butterfly matrices. So we found these two lines work kind of orthogonal to each other. So we're thinking about if we really want to have some neural network with only a single butterfly sparsity, can we try to have this FFT on self-attention and butterfly factorization on feed-forward networks? And because at that time there's no this look, I think this is GPT 201, so most people are still deciding whether we should go to encoder transformer, a decoder transformer. So we test this on this at that time we test this result on BERT, which is an encoder only transformer, which shows by have this FFT on attention self-attention layer and the butterfly factorization on these feed-forward networks. There's no accuracy loss on long range array data set, but we can achieve up to 60%, 60 times compression rate. So the result is very impressive, but I have to say this result is not a final conclusion because we found it's not very effective for decoder-based transformer, which is large language model. But here, as I mentioned, some conclusion already out of date, but I still want to show what is the key idea of algorithm and hardware co-design. So to support this butterfly sparsity at the hardware level, so this is what we explore at the hardware level. We propose a hardware unit called Unified Butterfly Sparsity Engine, which is you can say this is a kind of domain-specific engine like sparse tensor core. So it kind of have some key hardware features. For example, we make it a runtime adaptable, which means it can reconfigure to support both FFT and butterfly matrix multiplication to make it very compute efficient. And so this is a key idea. At algorithm level, we try this like apply this butterfly unified butterfly sparsity on the encoder only transformer BERT, and we can see impressive results. And we also try this. We also design this hardware accelerator. So we co-design both part, and we prototype on FPGA. And as you can see, this is the picture after the place and routing. And this is what I have done when I was interned in Samsung AI Cambridge. So as you can see here, we can beat most of the SOTA. So we can achieve nearly 4 times higher energy efficiency and 20 times lower efficiency because, as I mentioned before, this butterfly sparsity really reduce the algorithmic complexity a lot. So again, this is the work I have done during when I was a PhD. So this unified butterfly sparsity engine, and to our surprise, so we are trying to explore whether it's possible to integrate into this mobile NPU. And so another line of work I have done at Samsung is we explore this multi-tenant smart home setting. So we target on sparse multi-DNN workloads. So which means let's say you have home hub, you have the speaker, you have your laptop, you have your desktop. So each devices it has its own deep neural network request, and you're trying to schedule different neural network in this home hub setting. So in that paper, the key idea is we capture both static and dynamic sparsity. So we also like submit the artifacts evaluation for this work, and this work is later on published at Micro 2023. This is I think the first work after my PhD graduation. And we also explore this GPU reconfigurable accelerator. So let me just help you to recap my research until now. So we explore this efficient ML not just in a single stack. We try to explore in multiple stack and try to push this AI efficiency using cross-stack optimization. And what is next? So we're thinking next perhaps is a device level. So this is also something we're thinking. And so we are also exploring this 3D chip. So DRAM stack AI accelerator. We just have released an archive version in today for our 3D chip modeling for distributed large language model system. So yeah, so that's it for my presentation. Thanks.
Thank you very much, Hongxiang, for your wonderful talk. And any questions from the audience? You can unmute yourself or input a question in the chat box.
Oh, hi, Professor Fan.
Hi.
Thanks for your wonderful presentation. So would you mind going back to page 22? Oh, yeah, I have a small question about the problem itself. Actually, because you mentioned first you go along the left path, and then you go back to the starting point A, and you go back to the right path. So like the first one is A, B, D, G, and the second one is A, C, A, C, F, G. This is the original generation path is. So my question is, could you just like start at A and generate the B and C in parallel? Why don't you just generate B and C in parallel starting from
Oh,
A?
yeah. So basically this is the default setting. So
Mm.
we generate because you can also generate A, B, and then generate B, C in parallel, but the assumption is the limited memory, right? So
Ah,
if you generate A and B, C, so at next step you let's say you can just hold four nodes
yeah.
at one time. So for next step you still need to do eviction, right?
Oh, yeah. Oh.
So
In this
the
way,
assumption,
so
yeah.
in your optimized way, you minimize the eviction,
Yeah,
activity.
yeah, yeah,
Oh,
exactly.
yeah, yeah, makes sense. Yeah,
So the
because
key
of the
idea,
limited.
yeah,
Oh, okay.
yeah,
Okay,
yeah,
thank
the
you,
key
thank you.
idea is just
Mm.
reasoning path reordering to
Uh,
minimize or reduce the eviction. Yeah,
yeah, because the memory is very limited in the edge scenarios.
yeah, exactly.
Okay. Oh, thank you.
Hello, Professor Fan.
Hi, hi, hi.
Yeah, thank you for your talk. It's wonderful. As you do research in, like, I think in all four stacks, like system, algorithm, and hardware, I have very general questions about,
Mhm.
like, what's your philosophy, like research philosophy about system algorithm co-design, for like efficient AI, this kind of things. Because I think for many research questions, when you work on the efficiency problems here, you can always do like algorithm innovation or system innovations. But in one paper, like how do you organize your these ideas to find some what's your philosophy there?
Okay, I think the
Mm,
philosophy here is for some efficient algorithm, the underlying system support might not be good enough. So this is
mm,
kind of demonstrated in this XPLOS and Nuri series paper, right? So if we have an efficient algorithm, sometimes you need to change the infrastructure as well. So the basic philosophy, I'm not sure whether I answered this question properly, but the
mm,
basic question is like tailor your efficient algorithm to the underlying system, also tailor the system support to your newly designed algorithm such that you can have this extreme efficiency because only focus on one side you
mm,
might leave the other side inefficient. And I think the other example to help you to understand is like the DeepSeek, right? So the
yeah.
DeepSeek we have the R1. So basically, because they have the underlying hardware constraint, like they have the memory constraint, they are not able to train the original attention at a very large scale. So they propose efficient attention module to kind of tailor to their limited GPU system. So in that sense, they also provide the tailored system support for the efficient attention variant for that GPU system. So this is kind of core design philosophy. And the other example is if you watch the GTC from NVIDIA, I think Jason Huang also mentioned many times about this core design. So basically, it's just to kind of seek the efficiency on both sides instead of just one side. I'm not sure whether this answers your question.
Oh yes, very very, very good.
Yeah.
Yeah, always you have algorithm innovation. You should have very good system implementation. Always.
Yes.
Yeah, always space to do that. Yeah.
Yeah.
Thank you. Mhm.
Some other questions from the audience?
Hi, Dr. Fan.
Hi.
Yeah, I have another question. So I saw like you have many wonderful job work in the test time scaling and the diffusion language models. So I'm thinking of if like there is a possible interaction with these two different areas, like traditional test time scaling is mostly done on the autoregressive models, but I think the diffusion language models have some potential because it introduced another dimension, which is the time dimension. Like you
Yeah.
have iteratively diffusing like a block of the masked block. So I'm thinking of if we can utilize this extra dimension to maybe do some test time scaling kind of stuff to increase the model performance. So yeah, any insight will be appreciated.
Yeah, I think it's a good question. We actually we thought about this mid of last year when the diffusion language model was discussed a lot. So we think about this. And the first is we found maybe this is not the conclusion now, but it's just the initial experiment we have done at that time. We found the test time scaling has limited effect on diffusion language model at that time. I think we are playing with the LADA 1.0. If I'm not sure whether new models they will have different conclusion, but our initial experiment shows the improvement is very limited. This is the first thing. And the second thing is, I think there are already some paper, because I think our initial experiment shows negative results, so we stopped doing that. And in my group, there's actually another student who wants to do this direction. And at that time, we re-investigate this direction. We found that already some paper exploring this direction. And I think the result in that paper is also not very good. So this is our experience. I hope this is helpful. But if you're interested, yeah, well, I'm very welcome in any discussion later.
Okay, thank you for your sharing.
Yeah.
Any other questions from the audience? Okay, if no more question for audience, actually, I have some questions, yeah, to ask. And the first, Hongxiang, so I was wondering, so your works on those the edge LLM test time scaling is pretty interesting. And so your slides show that so the evaluation is on the AIME, the mass data set. So I was wondering how about that? So it's those the small LLMs performance with the help of test time scaling, some more challenging tasks like the practical coding environment and so on. Yeah.
Yeah, it's a very good question. So this is what we found. So it might help the coding a little bit, but the improvement is not as significant as math. Because I think this is not a problem for test time scaling. I think for most of reasoning tasks, most of research they focus on reasoning like math. So this is we also test in the coding task. I think we also include in our new riffs and S-Flaws paper. Like it's still some improvement. Yeah. But I think you're right. So this is something we also keep exploring. to see whether test time scaling can have a broader application to different, for example, agentic tasks. This is an active research topic in my lab.
So do you think why there's some kind of the gap between the different tasks, especially for coding? Because we know
I
right
think, yeah,
code major application, right?
I think it comes from the nature of the task itself. Like for some tasks, for example, they're easy enough, or like iterative thinking will not help in some tasks. And for some tasks, they are kind of very kind of structured. So as I said, this kind of tasks may be like coding. So basically, that's reason why diffusion language model will kind of have very high performance in this coding because they're very structured. And this reasoning process might not have as significant improvement to the math. So this kind of is the nature of the task itself, and it kind of case by case. This is my answer.
Okay. Yeah. And thank you. And another question is about your butterfly work. So I was wondering, is there any kind of like your kind of follow-up exploration based on that work?
Yeah, it's very good question. Basically, we have follow-up exploration, but it's negative results, so we didn't publish any. So we try these butterfly things in like the decoder only, like the GPT 2 or 3, and the accuracy is not very good. So basically, I guess this butterfly sparsity, it actually improved a lot of, I actually introduced a lot of information loss. So make it only work for some, because I think in here we test on encoder only transformer, so they are very good at like imaging related task. So this level of information loss introduced by butterfly sparsity is too much for decoder only transformer. So that is our conclusion at that time. But I think maybe things is different now. Yeah, but we stopped exploring after we tried this butterfly sparsity on decoder only transformer.
Okay, thank you. Thank you
Yeah.
very much. So any other questions from the audience? Okay. So if no more further questions, now let's thank our speaker again. So thank you, Professor Fan,
Okay.
for this. I know it's very busy schedule, and
That's fine. That's fine. Okay. No problem. No problem. Nice to talk to you guys.
yeah, yeah.
Okay.
And also
Bye.
to attend the talk and our next week because the speaker have some kind of the time of conflict. So our next week's talk will be rescheduled to this fall, and our next talk will be the 2 weeks later. So next Tuesday. So see you guys. Okay. Thank
Okay.
you.
Bye.
Bye.